Okay, over this video, I want to show off a couple things. This is one of my favorite guitars. It's a G&L ASAT, what they call the Z3. And I believe this is a 2011. I've had this guitar for a long time, and it's one of my favorites. The thing I've never liked about it is the pickguard that came with the guitar was a flat, black, pretty basic piece of plastic. Really no detail on it, no lamination. It's kind of a boring pickguard. I've always wanted to replace it with something else, and the thing that's unique about the Z3 is the shape of the pickups. There's 3 pickups, and they're each Z-shaped, and so I've never really had the time or really never had the inclination to figure out how to make this pickguard until I got an X-Carve. And with that X-Carve, I all of a sudden had all these great ideas about projects I've wanted to do that I now can do with the capability. So over the course of this video, I want to show what I did with the pickguard on the Z3, how I actually created the solid model in Fusion 360, and then how I cut it using the X-Carve. So stay tuned and enjoy. Thanks. Okay, so the first thing I did to create this new pickguard is I took the old pickguard and I scanned it. So you just used a basic flatbed scanner, and I scanned it. You can see in the picture here, I scanned it with 2 rulers because I learned something important. 1 ruler in the X and 1 ruler in the Y. I did this once. I created the whole model. I got it done. I cut it, and nothing lined up. Because all I did is I calibrated it in just one axis. I just calibrated in just the Y-axis. And the scanner that I have, it's an older Canon scanner. I use it for pictures and things like that. One of the axes was off a little less than 1% of the overall length of the scan. And if you're scanning a picture, it's probably not that big of a deal. But in this case, that little less than 1% in the one axis was enough to put the farthest holes about 70 thousandths off where they needed to be. So after some gyrations and some trying, I scanned it again with a ruler in both the X and Y, and then I was able to calibrate each axis and really scale each axis. That's the best way to describe it. Scale each axis. And then once I had the scaling done, I could calibrate it in the calibration tool within Fusion 360. So lesson learned. I should have, in retrospect, gone back and actually measured off the model against the pickguard that I have. Lesson learned. Okay, so I'm using Fusion 360 to create the solid model for this pickguard. It's a great piece of software, a real simple application to use. And if you're a hobbyist, you can actually use it for a year for free. So within Fusion 360, I'm going to insert the scanned image that I made of the pickguard. So I'm going to go to Attach a Canvas. I'm going to select the image, and it's right here. And then I'm going to put it on this plane. Now I've already done this, and you can kind of see there's a little small rendering of the image right there. The most important part about attaching the canvas, at least that I learned, is you have to scale it here. Now this doesn't scale it to the actual 1 inch is 1 inch. This scales the shape of the canvas relative to X and Y. With some trials and some gyration, again, I found out that my X-axis needed to be scaled 0.089% off of the Y. And that's enough to get all the holes back into alignment. And so I just here put my scaling factor here on the X and then hit OK. Now I've already done this, so I'm going to get out of here and I'm going to bring up, there's that canvas. So there is my scanned image. And so again, I scaled the image so that 1 inch in the X and 1 inch in the Y, or X and Y, are the same. But now once I have that, I need to calibrate it. So if I go under Canvases, I right click on that and I go to Calibrate, I need to use this ruler here to define 1 inch as 1 inch. And so I started here at the 1 inch mark, I made another mark here at the 8 inch, and said that was 7 inches. And so doing that, Fusion 360 is going to scale this so 1 inch on the actual picture corresponds to 1 inch actually on the solid model. So now that we have that done, I need to start defining the geometry of this pickguard based on this image. So the first thing I did was I created essentially the outline of the part. And so to do that, I just created a spline for all the complex geometry, and I just worked my way along to create the spline. When I scanned this, this edge right here on the ruler is my true edge, and I put the actual pick guard up against that true edge. So all of these lines are just straight lines. And then I just did a 3-point circle to define this shape here. That's actually where the pick guard bumps up against the switch plate. And same thing here, I did a 3-point circle to actually define this geometry here for where the pick guard wraps around the neck. So I take that sketch away. Again, you can see there is the actual shape of the pick guard. So with that done, my next task, I'm going to bring the picture back up, was to locate where the holes go. And so to do that, I just create another sketch using that, and then I did 3-point circles on all of the holes that are defined here on the pick guard. Now, there are burrs, and they're not the cleanest of holes, and so there was a little bit of just making sure I picked the cleanest geometry really to define the center of all these holes. These 6 holes here in the middle are the adjustment holes for the actual pickups to adjust them up and down. And then the holes in the perimeter are actually what hold the pick guard down to the actual guitar body. Once I did that, I went back and then defined the geometry for the holes for the pickups. And let me put that back there. And again, same deal, I used a 3-point circle to define the circles. Since I know this edge here is straight, I can define these just as vertical lines. But you can see something kind of interesting here that I learned too. Is with the scanner, there's a little bit of parallax because I put the pick guard down on the scanning bed with the side down that would face the guitar. So the image that I'm seeing right here is the side that would be against the guitar. And so I had to make sure when I was picking this geometry that I was picking the real edge that I want to use to define the shape. And so I have to kind of watch for things like these shadows to make sure I'm picking the right piece of geometry. And so once that was done, and I defined essentially those 3 major things, the outside perimeter, the actual location of the holes, and then the shape of the pickup, I created the body by just extruding the first shape by the thickness of the material that I'm using. I used the sketch that defined all these holes, and I created the holes for the diameter there. And then I also then extruded the shape of the pickup holes and cut those from the body. So the last thing that I did is I wanted to personalize this. I like to do this to all my guitars, and so I put the logo of all the guitars that I build here on the actual pickup. And so this is my Red Arrow guitar logo. And to do that, I just have this as a DXF. Just in the same way that I brought that picture in, I go to Insert, I can insert that DXF, and with that I define the geometry for this engraving. I extruded the shape to create this cutout here and extruded these stars. And you can see these are sunk in about 15 thousandths of an inch. So in about 20 minutes using the tools in Fusion 360, coming off that rendered sketch, I created all the geometry that I needed to make the solid model. So now I can create G-code to actually cut this. So let's get to that in terms of how we created the G-code to feed to the X-Carve. Okay, so now that I've got the geometry done, let's go talk about creating the G-code. So I'm going to go into the cam space in Fusion 360. And here's how I did the setup. So if I go back and edit my setup, the first thing I did is I went to the stock. Actually, no, let me take that back. The first thing I did was to go off and define the X and Y axes. So I did, for orientation of the X and Y, I did selecting X and Y, and I picked this edge here as my X axis, and I picked this here as the direction of the Y. And so I got that flipped so I had the orientation correct. Then I went to stock. And so in the stock, all I did was define that the stock side offset, so the width of the stock relative to the part, was 5 millimeters bigger. Once I had that done, I went back to setup, and then I defined this corner right here as the origin. So when I go to origin, I picked stock box point. I picked that point right there, and so that defines essentially where X and Y and Z are for the model. And then I defined the stock as about 5 millimeters over the shape of the part. So once that was done, you can see I've got these different steps here in the process. And so the first step that I did was actually to create the holes. And so when I go into here, I can go edit those holes. The tool I used is an 1/8 inch end mill. I took off any coolant. Again, I'm using an X-Carve. It has no capability for coolant. And I selected all the different holes here that we're using. And then the other important thing that I did is when I go over here into heights, I defined the bottom height as 1 millimeter under the material. So that way I know that I'm going through and I'm going to completely clear the hole. So I defined these holes first. I'm going to cancel this. I don't want to make any changes. Then the next thing I did was to define the actual tool path for the perimeter of the part and also for the pickup openings. So when I go into here, I can go back and edit that. I'm using that same 1/8 inch end mill. I played a little bit in some testing in terms of kind of optimum feed rates. I did a little bit of looking online for this type of pick guard material, and 300 millimeters per minute was about what everybody looked at. And then in this case, I did 2 passes. So I did a roughing pass. I did a roughing pass, and I made my smoothing deviation 0.2 of a millimeter. So what's going to happen is the mill's going to go off and cut the perimeter of the part, leaving 0.2 of a millimeter material, and then it's going to come back and do it again. Just whether it made a difference, I don't know, but it took no extra time in terms of milling time. And then the other thing that's kind of important is I made sure that for these types of plastic materials, I wanted to actually use conventional milling, not climb milling. So I checked that there as an option, and that was that step. From there, I wanted to put a chamfer on the outside of the part. And actually, I don't want to do everything. I only want to do a chamfer on essentially this flat edge here, this corner going this way, this corner going all the way around to here. And to do that, if I just press this and select it, you'll see it's going to highlight the entire perimeter all the way around. But if I press the Alt key, I can just select specific features that I want to be a part of this chamfer. So the other thing, and this took me a little bit of gyrations too, was the tool that I picked essentially is a 1/4 inch 90-degree spot drill. And so that lets me put half a 90 degrees, so a 45-degree chamfer along the edge of the part. And I also spent some time kind of working on this in terms of, and bear with me, I got to go figure out where it is, defining the actual shape of the chamfer. This chamfer width is actually to ultimately determine how much of a chamfer I'm putting on there. So in this case, after a little trial and error, I put 1.75 millimeters of chamfer width. It doesn't go all the way through, and it leaves a little bit of a flat edge on the underside here, but it was perfect for what I wanted. After I got the outside chamfer done, I also wanted to chamfer these holes here. Not the holes that are used actually to adjust the pickup height, but the holes in the perimeter of the pick guard that actually hold it down to the guitar body. So I did the same thing. I select just the geometry for those holes. I'm using that same 90-degree spot drill. And then in this case, I made it the chamfer width 1.5 millimeters, so a little less than what I did in the outside body. Again, the whole goal is just to countersink the screw, so the screws that hold the pick guard to the body are essentially flat with the top. So once that was done, I wanted to go off and create all the geometry for the engraving of the logo. And so I did this in 2 steps. I actually used the Engrave feature. And so let me go into that. The Engrave feature to define the actual shape of the arrow. And I'm using a 1/32 end mill. And I picked these 2 paths right here. And the Engrave feature, which you can see is actually under here. Let me get out of here. The Engrave feature within Fusion 360 we'll take two pieces of geometry and we'll find the center between the two. So I pick the inside and the outside, and it will define the tool path to cut that. Once I did the arrow shape, I wanted just to clear out the stars. Again, this material has a black layer, a center layer of white, and the bottom layer is black. And so I wanted just to carve out the star shape so you'll see them as white. The actual arrow will be white, and then you'll have the 4 white stars. So to do that, I actually used the 2D contour option. And let me get into here. I'm going to go and look what we did. Again, I just select this shape here. And again, it defines the tool paths to go off and cut out and clear out the material for those stars. So again, very fast, very efficient. I was able to define the tool paths to cut the holes, to cut the outside perimeter and the inside features for the pickups, chamfer only specific geometries on the overall shape, chamfer only the holes I wanted to, engrave this arrow shape, and then also clear out the white area here for the stars. So once I did that, it's really easy. I select it. I can go here to post-process and follow that process to actually create the G-code that I'm going to put into the X-Carve. So now that we've got that done, I'm going to cut to some video actually showing the machine cutting the pickup, and then we'll come back and look at the finished product.